Assalamualaikum everyone. In today's episode, we focus on a follow-up of a past upload on resonance in a closed and an open pipe. This time, we look at the case of a mechanical system that undergoes resonance, consisting of a string instrument and a stock organ pipe. So join me till the end of this video. Watch and learn. The question is, one of the strings of a bass viol is 0.680 meter long and has a fundamental frequency of 165 Hz. Letter A. What is the speed of waves on this string? Letter B. When this string vibrates at its fundamental frequency, it causes the air in a nearby stop organ pipe to vibrate at that pipe's fundamental frequency. The speed of sound in the pipe is 344 meters per second. What is the length of this pipe? The string instrument described in the problem is a bass viol, an old musical instrument of the viol family held on or between the knees where the tension on the strings can be increased or decreased to adjust the pitch of each of the strings. And the other instrument is an organ pipe, a stop pipe, one that is closed at one end and open on the opposite end. One of the strings of the bass viol has a length 0.680 meters, and it has a fundamental frequency of 165 Hz. When this string vibrates at its fundamental frequency, it causes the air in a nearby organ pipe, which is a stop pipe, to vibrate at that pipe's fundamental frequency. And the speed of sound in the pipe, or we also consider that as the speed of the air columns in the pipe, equal to 344 meters per second. And our target variables are, in part A, the speed of the waves in the string denoted by V sub S, and in part B, the length of the pipe denoted by capital L sub A, meaning the length of the column of air in the pipe. Recalling our past lesson on resonance of standing waves in stop and open pipes, for a stop pipe, the only normal mode frequencies are the odd multiples of the pipe's fundamental frequency. The frequency small f sub n is equal to the product of an integer n multiplied by f sub 1, or the fundamental frequency, and the corresponding wavelength lambda sub n equals 4 times the length of the pipe, capital L, divided by the integer small letter n, where this small letter n, okay, is an odd integer, either 1, 3, 5, and so on. On to our computations. In part A, we compute the speed of the sound wave denoted by piece of S, right, in one of the strings using this formula for relating the fundamental frequency, the speed of the wave, and the length of the string, right? So we derive by isolating uh, V sub S and come up with the working formula. V sub S, or the speed of the wave in the string, right, equal to twice the product of the length of the string, 0.680 meters, and the fundamental frequency, f sub 1, 165 hertz. So when you simplify this, we get the value of the speed of the wave in the string equal to 224 meters per second in three significant figures. Notice that the speed of the standing wave in the string is less than the speed of sound in the pipe, right? This is primarily because although the fundamental frequency of the vibrating string is equal to the fundamental frequency of the vibrating air in the pipe, their respective wavelengths are different. The wavelength of the wave in the vibrating string is less than the wavelength of the sound wave in the pipe. Lastly, in part B, we compute the length of the closed pipe denoted by capital L sub A based on the equation F1 for air, or air coulomb, is equal to the speed of the sound in the air coulomb, or the pipe, that's V sub air, divided by 4 times the length of the air coulomb, or the length of the pipe. So isolating for capital L sub A, we have the length of the air coulomb, or the pipe, capital L sub A, equal to the speed of the wave, all right, in air. That means uh, the sound that is produced by the pipe, its speed is V sub air, and that is divided by 4 times the fundamental frequency of the pipe, or the air coulomb in the pipe, F sub 1. So when you substitute, we have capital L sub A equals 344 meters per second divided by 4 times the fundamental frequency, 165 hertz. So doing our math, we arrive at the value of the length of the pipe, or the air coulomb in the pipe, capital L sub A, equal to 0.521 meters, also in three significant figures. Before we end, let us stress the key concept that we have applied in this problem. If you force or drive a mechanical system, such as a guitar string or the air in a pipe, to vibrate at a frequency F, the system will oscillate with maximum amplitude. In other words, it resonates. If the frequency f equals one of the normal mode frequencies of the system. So that concludes our lesson on this topic. Till the next episode, mabuhay, mashallah. Thank you very much for your indulgence. Please don't forget to subscribe to my YouTube channel. Alhamdulillah.